What's a random number and why should I care? I gave this talk at ACCU 2023 and some random things happened, so I'm doing a special recording for you now today. What is a random number? Well, Stack Overflow comments suggest that you can write a function that returns a perfectly picked random number, 59. Some XKCDs that maybe pick 42 instead. Is this a random number? It might be. Well, it can't be really, because to answer the first question, what is a random number? There's no such thing as a random number. You can have a sequence of numbers that might be random, and the sequence, even though they might be random, might still have properties. We can look at the mean or expectation, the variance, and similar things. Just of note that chaotic isn't quite the same as random. We'll look at that in more detail soon. Mostly we'll be talking about pseudo-random numbers during this talk, but we'll just touch on some crypto stuff as well. Now, if you've got a sequence of allegedly random numbers, can you tell whether it's actually random or not? I think the answer to that question is no. You can see whether it's likely to be, but that's about it. And let's go back to basics. John von Neumann said when people started thinking about how to generate random numbers from computers, that anyone who attempts to do this is living in a state of sin. It does seem ridiculous to call a function once and expect to get different answers each time. Normally that would be a bug, but that's what we want when we try and generate random numbers on a computer. Why should you care? Well, people get things wrong. They use random number generators incorrectly. Some of the random numbers generators aren't brilliant. We need randomness for a variety of things. To make games interesting for starters. And then we use them in a variety of simulations, from pricing financial instruments to, for example, COVID modelling, which is based on various infectious disease dynamics. You can see in the diagram mentions of R numbers, which might ring a bell for some of us. And those are numbers we'll plug into a model that influence how random numbers are spread out over various ranges. But you should also care if you're trying to test code with random numbers in. And I suppose that begs the question of how we test random number generators themselves. So let's look at why you care. If you've met me before, you might be familiar with me trying to code my way out of a paper bag. I've got a certificate that says I can code my way out of a paper bag. Let's assume you've got a paper bag indicated by the brown edges and, say, 3 green blobs, perhaps. Let's have a demo. If they all move at the same pace, well, they're going to escape the paper bag for sure. And we're nearly there. And we're there. Marvellous. Trouble is, that wasn't very interesting. So why we care is we can make things more interesting with some random numbers. We'll do that later on. How do you generate random outcomes? Well, obviously it depends which language you use, but most languages support some kind of random number generation. We've got slightly different APIs. So, for example, if you want a random number between 1 and 6, you need to work harder if you're using C. Python will help you out there. If you want C#, you can call random.next. If you call that between 1 and 7, you get a number between 1 and 6. Some languages have got some security cryptographic random number generators bolted in. Some languages like R support not just integers, but give you normal distributions of doubles and floats as well. So if you switch between languages, you have to stay on your toes a bit. whatever you're doing, always ask two questions, particularly as you switch between languages. Is the random number generator default seeded, or do you need to seed it yourself? And does the range include the upper bound or not? Let's look under the hood and see what's going on when we generate random numbers. Yep, that is a car full of walnuts, which is slightly random. I think the squirrel put it there, but what can you do? How do you generate random numbers? This dates back an awfully long time. A surprising number of things in computing date back to the 1950s. So we'll start with what's called a linear congruential generator. Two words, linear, so we can see a xi plus c, which is like the y equals mx plus c to get a straight line, hence linear. Congruential, we're doing modulus. That has the effect of like appearing to chop around in a number sequence. The simpler case of these are just the multiplicative linear congruential generators. So instead of adding a c on the end, we've just got something to multiply, and a modulus. So we need to be circumspect when we choose these two numbers. You almost certainly want m to be a prime, and you can use a Mersenne prime, which is 2 to the power of another prime number, subtract 1. And then the multiplier, a in this equation, takes some tinkering with to get right. So if we just think about multiplying one number by an a and then finding modulus n, what happens if we take m is 11 and a is 7? If you work through the maths of that, you'll see we can get 10 different numbers. As soon as we hit 1, we then stop repeating, so we get a cycling sequence. If I choose a is 5 instead, we do the maths, we're going to collapse down much more quickly. And if we aren't careful about using prime numbers, which means we could have a and m having common factors, so if a is 4 and m is 12, for example, if we start with 1 again, multiply that by 4, okay, we've got 4, so we've got a 1, then a 4. If I multiply that by 4, we get 16, modulus 12 is 4. So now I've got another 4. So I've collapsed down and I will get 4s from then onwards. If a is a multiple of m, well, we collapse down straight away. So start on 1 and then we drop to 0 as soon as we do the modulus. So there's a variety of ways of these collapsing. And even if they don't collapse immediately, the cycle size or the period of the generator might vary. So now you can extend these out. A more modern version is a Mersenne Twister. Now, okay, it's got precise mathematical definition. What it's doing is it's taking some chunks of several of the previous numbers and concatenating some bits and doing some exclusive ORs, which then gives us twisting around of the bits where we're shifting some things or not, depending. Because that's using several of the previous numbers, if I see 1 once, if I see it again, I might not get the same number next time, so I might get much more variety. There are other kinds of engines too. You can do a lagged Fibonacci, which uses 2 of the previous terms rather than just the previous value. And you can drop some bits out, you can shuffle things around. So lots of different engines to help us generate random numbers out there. A lot of languages are using a Mersenne Twister, and some of them are still using the linear congruential one, which is fine, and they're good enough for many things. We'll look at some cases where they might not be useful later on. So we mentioned a being possibly 7 to the power of 5 earlier on. That, if you look through the C++ random header, you'll notice the 16807 in there for minimum standard rand 0, which probably wasn't its name originally. And that was updated in 1993 to use a different value for A. There's things about how often you tend to get the same number in the same place, which you can see with spectral analysis, which we'll look into later. Maybe the minimum standard's slightly better. There are other things out there too. In fact, we've not seen any changes in the C++ random number generators for a long time, but there are some proposals out there to try some different, to have some different generators. I noticed recently that Python's NumPy was using a Mersenne Twister and they've switched to a new one, so just keep your eyes on that. So this proposal to introduce new generators to C++, as I said, pointed out that we've got various different generators and they've been stable since C++ 11. We've got the linear congruential ones. They've got short generation periods. So things start repeating. Once I see one once, next time I see it will I'll get the same sequence of random numbers happening. The Mersenne Twister behaves better in that sense, but it's using a big state vector, and that means you can't do GPU stuff like CUDA particularly easy because you've got too much state to shovel onto your graphics card and get back again. And quite often you actually want what's called quasi-random numbers for Monte Carlo simulations and similar. So if you're doing things in finance and you want, and epidemiology as well and others, I would imagine, if you want plus something, if you get minus something as well, then you're more likely to equally cover the whole possible search space you're looking at. And you can't do that particularly easily with C++ random number generators at the moment. So on the side, we've talked about linear models. If you open your mind up and try squaring things instead, so for example, do x squared take 1. Again, we can do the maths. If I start with 1 in the left-hand column, square it, 1, and subtract the 1, I get 0. Then 0 squared subtract the 1 is minus 1. Minus 1 squared is plus 1. Just take the 1 back to 0. And a flip-flop between 0 and minus 1. Similarly, if I start at 0, well, that's come out of the sequence we just investigated, so flip-flopping. If I start with a different number, I get some more interesting things to begin with. And then that collapses down as well. But as you shove the starting number across, you start to see different patterns. You can flip it on its head. Suppose we start with z is 0, and we use complex numbers this time, which is just a number with 2 parts, and allows you to do magic like find the square root of minus 1. So we'll pick a complex number, so instead of subtract 1, which we had in the last slides, we're going to subtract a complex number. We'll plot the complex number, so it's got 2 parts, so we can draw it on XY plane. They're either going to cycle, or they'll collapse down, maybe end up at 0 or similar, or they keep growing, in which case we'll colour them in. Some of you might recognise the shape we get. Now, we've got a recurrence relation, so there's nothing random going on there at all. But this is the root of many models of chaos. One small change will flip you between the coloured part and the dark part. Tiny little change, and it's really quite difficult to work out precisely where you are on the boundary. That's chaos. It's actually coming from this recurrence relation, which we're using to do random things, which aren't the same as chaos. Oh yeah, you can try 2 times x squared minus 1 if we stick with the 1 this time, and you'll see some sequences are the same, or with different starting points you see things flip-flop around quickly. And in fact, some of the cryptographic numbers used start investigating things that are non-linear. However, let's go back to how we use our pseudo-random number generators. It's time to think. Let's look at some possible problems, some common use cases. Let's have a think about testing. Because if you've got some random behaviour in your code, how do you test it's behaving properly? So we've seen the recurrence relation. We start with a value for x and then make the next value. What do you use for the start value? That's called a seed. We'll look at that. Be aware that if you use the same seed in different languages, you might well get a different sequence of numbers out. Or even if you use the same language but a different operating system or a different compiler or interpreter, you might get different numbers. Or a different version of the language, you might get different numbers. So using the same seed does not guarantee you know exactly what you're going to get out. It depends. Something else to be mindful of is if you are using threaded code. If you use C's rand, it might not be thread safe, which is why it's started to be deprecated from C++. There are newer, better ways of doing things at C++11. If you've got two threads kind of sharing a generator, even if you're not using C, the order you get the numbers out in might appear to change because you don't know which thread it's likely to turn up on. That's really good talk on Microsoft's website about why RAND might be considered harmful if you've not seen it. Not just about threads. We'll see some details in a moment. Okay, let's do some basic stuff. We said random made games more interesting, so some games involve rolling a dice. For roll a die in Python, I've got options. If I use randint, I need a randint between 1 and 6 inclusive, but I could use rand range, and then it's between 1 and less than 7. So you've got to watch yourself there. Ask yourself two questions. Is it default seeded? Yes, it is in Python. And that is the top one included or not? Well, in Python, it depends which function you call. You can't say I want a number between 1 and 6 with C it's rand. So how do we deal with this? First, C's rand needs seeding. If you don't seed it, you're going to get the same numbers each time. You could use the time to seed it if you want. We'll look at that in more detail later. Lots of people will take the random number and do modulus n. Trouble is, if I've got 6 numbers, that probably doesn't go into random max plus 1 an even number of times. So some outcomes are going to be more likely than others. That might not be noticeable in a game of dice, but it will skew your numbers slightly. If you concentrate, you can do the right thing and stop that happening. Yep, we need to do some adding and dividing and concentrate hard. Well, you can use C++ instead. We need the underlying generator, and we've talked about those. We've got the default random engine, which is usually a Mersenne Twister. And now we want a uniform int distribution between 1 and 6 inclusive. And then we just call the distribution with the generator, and it gives us the numbers. Okay? Now the default random engine, as we said, is a Mersenne Twister that's put these magic numbers in for state, which comes from a more general Mersenne Twister. And if we dig into the constructor for that, we've got a static const_exp, which is being used as a seed. And then the default constructor will call the seed with the default seed and another number for state. seed the engine for us. That means we haven't chosen the seed ourselves, so if we run it twice, we get the same sequence of numbers. Bother. So, seed your engine. There we go. We can use random device, which is finding the entropy from your operating system. And we just send that to the constructor of the engine. And then we're off. Yeah, and notice previously we'd specifically said we'd got a uniform distribution of integers, but we don't need to do that because we've constructed it with 2 integers. This time, I run the code, it will behave differently each time. What else can we use to seed things? Oh, I could use now's clock, the current time from a steady clock, for example. And that would in fact be fine in the last case. It doesn't always work. If you want to seed 2 generators in quick succession, they might end up with exactly the same seed. We'll come back to that. Questions about how you seed things. There's a variety of things out there on the internet, some of them more helpful than others. We've been using a random device and using that to seed our engine. But that will only set some of the state. That's going to leave out some of the possible state that we could have had for the Mersenne Twister. And that means that you won't get the full gamut of all the possible outcomes. You've narrowed down what might happen, which is fine for games of dice and cards, and even a few Monte Carlo simulations if you're just doing some small things. Now, it's weirder than that. So we said this Mersenne Twister's got quite a lot of state going on, which is why it makes it hard to use for GPU stuff. And you can play around with it. There's 2 ways to seed it. One, we've seen seeding with just 1 number, and then it sends this second number in via the constructor. If you use this alternative way of sending a seed sequence, that's several numbers, you'll never get a 7 or 13 out first. And several different numbers will produce the same ones in the same place. So, does that matter? Well, right, so if I use the seed sequence, so I'll send in a sequence of 1 or more numbers, I do not get 7 out. But if I just use that number directly, then I do get 7 out. Does it matter if you never get 7 first? Maybe, maybe not. It depends what you're doing. It does show that we've narrowed down the state that might happen if we're not careful. Some people have suggested doing a warm-up, so you can discard several numbers from a sequence. Which I suppose if you did that random, you might think that's making it more random. Someone's written an academic paper on this and came out with the 700,000 magic number after a lot of experimentation. But the seed sequence is doing the warm-up for us. It's filling in all the bits of states. There's no point in doing that. Anyway, all that different ways to seed things notwithstanding, look, just using a random device and shunting it into your engine is fine. It's good enough for most simple things, certainly the things we're going to play around with today. And even some little artificial intelligence experiments or some games, it's absolutely fine. If you were doing some huge Monte Carlo simulations, you might need to think twice. Maybe use the seed sequence instead. You might get more variety each time you run things. It depends how many runs you want to do and how much difference you want. If I want to generate 2 dice rolls, can I use the same generator? You can probably get away with it and you won't notice, but Python again, you can make 2 generators people tend to go random.randint in Python. But rather than going to the kind of one instance of random, you can make your own as well. Just saying. Okay, how do we roll 2 dice in C++? We said seeding things with the current time might be bad. Here we go. Make 2 random number engines and use the current time for both of them. One instruction after the other, highly likely to end up precisely the same seed and come out precisely the same numbers. So, random device again. Seed that. Might get different numbers. You might not. Thing about a random device. Random things happen. Check. See what happens. But this is preferable to using the current time. We can make one distribution and draw from it. Or we could equally make 2 distributions. Whereas we're sending 2 different generators, so we don't need a second distribution. We could use the first generator over and over, but 2 generators, why not? Pick a card, all right? Between 1 and 52 cards, simples. Default C, inclusive or exclusive of the upper number. That works for Python. It's seeded for us, so we get a different card each time, maybe. And we'll get all 52 possible cards. But you normally shuffle cards first, right? Now, I can do random.shuffle on a list of numbers. I've just done 5 here rather than 52 to save some typing. And we expect to get all 5 of them back in a random order. Be careful. It depends what you're shuffling. If you've got large sequence, for example, if you're sequencing some DNA or something pretty huge, you're going to run out of space. The most number of permutations might be larger than you can get out of a Mersenne Twister or whatever generator you're using. So just watch out. How would you implement shuffle yourself? 3 cards, pick one, then pick another one, then pick another one. If you do that, the first one can be one of 3. And then from one of those 3 choices, you have a further 3 choices. And then finally, each of those 9 choices gives you a further 3 choices. So you've got 27. But if you write down all the permutations of 3 things, you should only have 6 outcomes. So what's gone wrong in our pseudo C# loop? We're reusing some of the cards. That's not what we're supposed to be doing. We're to be shuffling the cards, not generating new cards. There's a known algorithm for this. If you start at the end, once you've picked 1, you don't reuse that. Then you can go to the first 2. You've only got 2 to choose from there. And then finally you've got 1. So you get 3 times 2 times 1, that's 6 you need. Fortunately, C++ has a random shuffle. Well, had a random underscore shuffle. Some of these used modulus, and we've already cancelled ourselves against doing that, so it doesn't divvy things up into buckets equally. So that's been deprecated, now there's standard shuffle. And we can either use the standard shuffle or ranges version of shuffle too. And we pass the generator to it, so we can either have that seeded with a known seed or a random device, or the clock time if we want. That does the right thing for us. Okay, having shuffled the cards, pick a card, or pick a red or blue marble out of a bag. Python, list of things, some of them red, some of them blue. We can sample the things, and that'll get us one thing, two thing, third thing without replacing them. We can choose, so we can pick one, put it back, pick another one, put it back, pick another one and put it back. Simple, right? Good. How do we do this in C++? Got a vector of things using the string literal S for a vector of strings of things. Seed and engine, ranges shuffle. And then pull out the top three. Great. That works. I've now chosen three of things. Is it great? It works. But if we want to sample 3 integers out of 1 billion, we've got to shuffle all billion of them, which is over the top, right? Some people said, well, you could put everything in an unordered set and then pick out an index at random, or however many numbers you want from the to index into or select. We've got repeats, so that doesn't work for us. And it turns out, actually, if you pay attention, C++ has now got a standard sample since C++ 17, or the ranges version since C++ 20, which will do things much more efficiently. We don't have to resort to trying to shuffle everything and then just picking the top three. Moral of that story is keep an eye on C++, because things change and we get some useful functions introduced. Just, keep up to date. Start reading the documentation on this, you can certainly end up with your head exploding at least as much as mine did. What's going on in the sample? Well, it might do one of two things. Just throwing this up for something for you to muse on. If you've got a stream of incoming data and you want to randomly choose, say, 3 items from it, if it's a stream, then how do you pick some of those? Anyway, yes, that would be a whole talk in and of itself. We've done the sampling, how do we do the choices? Well, so this is with replacement, so I could pick the first red 3 times rather than 3 distinct reds. Well, what I can do is a discrete distribution here. I can make each of them equally likely by giving them a probability of 1 over the number of things. And then I can use standard generate to pick a random index from the things and slap them in a vector, say. And then I have my things. I think that's all right. All right, now we'll talk about testing as well. How do you test a dice game, picking a card, shuffling a card? You don't need to test your language's random number generator. I think a lot of times when we write tests for code that uses random, we end up saying, well, I get 1 out of 6 times when I roll a die. You shouldn't be needing to test the properties of the random number generation. You need to check you're using it correctly, though. So you can send in a known seed. You completely mock out the random functions. And if you mock them out, what do you do? Something that I found really useful on many occasions is providing a function that always sends in 0. If you've got some complicated maths happening, then a lot of the time, if there's a 0 in the middle of the function using the random number, you might get 0 at the other end, and then you can probably do the maths in your head with pencil and paper and know what you expect. Now, the seed will give you a known sequence caveat using the same compiler, same platform, etc., as we mentioned earlier. Will it cover transitions between all the states you've got? Might not. Like I said, you can fake this out completely and just send in 0 instead of something that generates random numbers. It might be worth separating out where the randomness is selected to the function that uses the randomness. What you're probably trying to test is if someone's won or lost a game of cards or dice or whatever it is you're doing. And that's going to depend on the actual number that's generated. So mocking it out is often good. And yet people will frequently have a test suite that's got a known seed, and then if they upgrade compilers, they rebase all the tests. I'm not saying that's not useful, but if you're doing some unit tests, what you want to do is test whether or not you do the right things with the right numbers. You don't want to have to keep changing the code to re-record what happens if you change versions and so on. And if you switch 2 lines of code, then you might get a slightly different number out the other end. Are you doing the right thing with the right numbers? Ignore the randomness. Let's look at some questions shamelessly nicked from Stack Overflow, just as a place to think about things. So, a couple of Python questions coming up, but you can think more generally in any language. If you've got some game that decides what to do if you try and hit an enemy in some game that does the call to random inside the function to work out what the damage is, how would you test it? The answer on Stack Overflow will say we test player hit missed. Test player hit missed. We test whether we get the right thing happening when the hit function misses. So we patch out the random number generator we saw in the last slide, and we go, yeah, monster's life is now 55. I don't know what the monster's life was to begin with. I don't know what it's doing with Scream. I don't like the test name. If the function on the previous slide took the damage, then you could test the hit with a different damage, and you could try like -3, whatever that is, 0 and presumably +3, and show what happened. I think you wouldn't need to patch out the randomness. You were checking you were doing the right thing with the right numbers. Yeah, send in the values. Another one. So somebody wants to return the index of a maximum value. If the value appears more than once, choose one of its indices randomly. Again, it's in Python, but we know how to rewrite this in C++. So they shuffle and sort and then take the first. Answer, somebody said, we'll just patch out the random shuffle of a lambda that doesn't shuffle anything. Okay, I'd be tempted to leave the random shuffle in there at that time and say, look, does it find the maximum value? If I've got 4 repeated in there, or at least get a 4 out. You could start checking it, may all give you 1 4 or the other 4, but then we're starting to test the random number generator behaves properly, which we don't need to do. Be more interested to see what happened if the list was empty. That needs more thought, I think. So, don't forget the edge cases. Maybe send in some specific values, or send in that value and then you can call the code somewhere else with random. But just check it does the right thing with the right numbers. Now we know random sequences have got various properties, so you can look at what averages you expect. And is your random uniform distribution giving you uniform results, particularly if you're doing something like attempting to use C's rand. Check you've done that right. We can use non-deterministic things to find bugs. I mean, property-based testing and fuzzing are important things, and that's generating some random inputs for us. But there's not space or time to talk about that today. Or even just simple things. Get your unit tests to run in random order. Whatever random means. We still don't know what random means, do we? But if they run in different orders from time to time, you might flush out some dependencies between your tests you hadn't even noticed. So try that. Oh, we've looked at card games and dice games. So we've looked at whole numbers that are equally likely. So there's uniform discrete distributions. You can have continuous distributions too, so things using doubles and floats. I've left a link to Richard Harris's website there, which is no more. Perhaps we'll get that resurrected one day. But yeah, there's uniform distributions and continuous distributions. There's discrete distributions and continuous distributions. And uniform ones, so things equally likely, or things that are weighted. Some make one or two of the outcomes more likely than others. Or maybe it's more likely to be around the middle, or maybe more likely earlier on, and so on. If you want to find a random angle, then we need to do some different maths, but we haven't got time to go into those today. So we've been using the uniform distribution, for example, for rolling a die. Roll it 120 times, you'd expect about 20 of each possible number. You might not get exactly that, but it kind of be flat, uniform, if you plotted the frequencies. Other distributions, and so for example the normal distribution or the bell curve, so you've got the characteristic shape there. If you divvy up the numbers you get into buckets, you get your frequency. You've got far more in the middle than out at the edges. And this, like all distribution functions, is a function that's applied. You think of it as being applied to that base engine, and it splurges out the numbers to make the shape we want. So they're all, if you look up any of the distributions in C++, you'll see a formula that tells you how the numbers are spread out to make the shape you're after. Which is, now we know a bit more about random numbers, that means we can have a race of blobs. This time we're going to have the green blobs as we had before, just stepping lockstep going up. Then we're going to have some cyan blobs that are drawn from a uniform distribution to decide the step size. They go between 1 and 40, maybe pixels, depending on what size I make the screen this time. And finally, we're going to have some normal or bell curve distributed blobs. They're going to have an average of 20 and a standard deviation of 10, which means they might actually go backwards. All three cases we've got an average of 20, so on average we can't tell who's going to win. Go. And the steppers are in lockstep, and we've got some normal blobs out in front, but one of them just went backwards and the cyan ones are trying to catch up, and now there's one in the lead, and all just nudged at the post. One of the normal blobs zoomed into the first place. But on average, we've set this up so they're all equally likely to win. Tremendous, much more interesting than the first race, I think. Now, that was fun. How do we test random number generators? Thank goodness we don't need to. There are batteries of tests out there, including a set called Die Hard, which covered some of the properties we want from random numbers, but not all of them. So, a new version called Die Harder, and more have been added over time. Just basic stuff we saw at the beginning. If I'm not careful, I don't necessarily get all the numbers in the range if I choose the wrong value for A when I'm doing the linear consequential generators. So, can I get all the numbers in the range? Are they all equally likely? We need that for the engine. We can splurge them out with a function to make normal distributions similar afterwards. But the basic engine want all the numbers to happen with equal likelihood. I mentioned about changing the value of A between a standard random linear differential model version 0 and the next version, no random number on the end, if you see what I mean. If you start plotting some of these things, if you plot one number against the last number, you can plot that in space, and you can see the graph on the left, they're quite regularly distributed, so you can almost see like spectral lines happening. But in the second case, using 13 to multiply by instead of 3, you get greater distribution in space. If you go to random.org, there's an example where I think somebody was playing around with a PHP random number generator, and in some cases you see the spectral lines on the right, which means you aren't getting the true randomness, whatever that means you're after. Whereas if you get what looks more like a random or white noise on the left, then it's a better random number generator. You can do this without eyeballing a plot. You do some spectral analysis mathematics to tell the properties of what's happening, but that's been part of the battery of tests for us. But you could plot this x against the previous x yourself and see what you get. What's the difference between a pseudo-random number and a securely generated random number that's suitable for cryptography? Well, I found a picture on Stack Overflow that's suggesting pseudo-random class using the clock time, Bosch pseudo-random number. And we've already said you can plug some OS entropy into one of those instead with our random device, and that might be better. The important thing is what's happening in that random class or that crypto class. I haven't got time to go into how crypto works, and I barely know the basics, but often it's doing something more than just linear things. Hinted at the something squared happening, and that gets used, but it's much more complicated than that. And fascinating talk for another day, I'm sure. But don't use the pseudo-random generators if you're trying to do cryptographically secure things. It won't be good enough. Someone will get hacked. What does entropy mean anyway? Obviously pulling on an idea from the real world, from molecules moving around. And Claude Shannon defined it as a level of information, or, well, surprise or uncertainty. Perhaps surprise is a better way. A surprising number rather than a random number. Yeah, it's still not defined random, but surprising might be good. Why not disambiguate it from chaos, though? Claude Shannon gave a precise mathematical definition of entropy. Basically, the bigger the number, the more entropy you've got. Don't say chaos because, well, maybe I should. I don't know. If you've got a completely unfair coin that always comes out tails, you'll end up with an entropy of 0. That means there's no surprise there at all. Which means, actually, you could do some kind of compression algorithm quite easily if you were transmitting data about coin tosses, whether you got heads or tails. You wouldn't need very much information to come down the wire about the unfair coin. In fact, you don't need to you could maybe just say unfair, and then the receiving end knows they're always going to see tails. Whereas for the fair coin, you'd have to transmit each outcome. Which means that some people have been using WinZip to see whether a file of values are random or not. Okay, random can't compress easily. Well, maybe. I wonder if I gave you the numbers generated by one of C++'s random engines, if you'd be able to figure out which engine I generated it with which parameters. You probably could. That's part of what the crypto stuff's driving at. Talking of cryptography, so there's some guidelines for what sort of things work and what sort of things don't, which are an interesting way of finding out even more about pseudo-random number generators. But things go wrong with these as well. Whole tales of stuff just on Wikipedia about things that have gone wrong in the past. We said C#'s got some secure random number generators, so it's Java, but they've been used incorrectly as well. Now, okay, we can try and use entropy for our OS. What about quantum computing? Recently seen what's described as an integrated balanced homodyne detector, which is using some quantum stuff, which allows for the creation of truly unpredictable numbers due to the inherent randomness available in quantum mechanics. Truly unpredictable, perhaps that's a good definition of random. Started thinking about this talk as I was reading Does God Play Dice by Ian Stewart. It's a very old book now. It's worth a read, and he's focused on chaos and the mathematics of chaos in there. And asked the question, like, is this actually random? Well, no, it isn't. We've seen that chaos is not random. Also seen that random isn't random, and we don't know what random means. I've had to randomly re-record this talk because my laptop randomly died live on stage in Bristol this year. I don't think any of these things were random. They were surprising, difficult to deal with sometimes. But sometimes random things are amusing and fun as well. Whatever random means. Good book. Give it a read. What have we learned? There's no such thing as a random number. You might have a sequence of numbers that are hard to predict. C++ gives us choices of engines, and maybe there should be some more later on. And we've gradually seen choices and samples introduced, so things change and keep on learning. Seemingly arbitrary outcomes make for good games. They can be used for, like I said, epidemiology and other useful things too, and they're fun. And yes, we've got time for one more demo. So this time we're going to add in some jumps. This gives us a whole number from a distribution. So you think of it as a number of buses that turn up in the next minute. That's a typical use case for a Poisson distribution. This time we've added a fourth block. So this block's going to be blue. Let's get that set up. Okay, and the other three will behave as before. The blue one is like a stepper, but it might jump. So it's doing 20, but it might jump a little bit. Maybe 1 in 32 times. Bring these guys over here. Sort of thing. There we go. And they're off. And there was a jump. The dark blue one on the left definitely jumped. And there's a cyan one going backwards. And the green ones are just doing their thing. And the uniform one's trying to race the jumper. And the jumper just jumped and just made it. Well, there we go. Much more exciting than the steppers just stepping. Random's fun, even if we don't really know what it means. Done our blobs. Used lots of random number generators throughout my career. I pulled together a small subset of some AI models on simulations as well. They're all reliant on using some random numbers. I think you could argue almost all AI has got randomness happening under the hood, even if we're not sure what random means, or artificial intelligence for that matter. And I had I've been writing a C++ book for Manning just to help people get back up to speed with stuff you might have missed since C++11, which is examples of using random number generators in there. And some of the things we've seen where vector knows you've put ints in it, so you don't need to do angle brackets and other small little things and some other useful bits. So that's me. Thank you for listening.